Hello students, welcome to Unit 3 Notes, Section 3.2. I already did the warm-up to save time, so at this moment, if you want to pause the video and you can write this down or try it on your own and then check over the answers with my own. But I'm going to start to explain it. So this is asking us to use the definition of the derivative to find the derivative with respect to x. So what I do know is that the derivative, or the definition of a derivative, is equivalent to the derivative, which is equivalent to limiting a function with respect to when h approaches 0. This is all connected. So slope is equivalent to dy dx, well, delta y over delta x is equivalent to dy dx, which is, oh, I have this in the wrong order, equal to dy dx, which happens when I limit this function is 0. It doesn't really matter. All of these are equivalent, but we're gonna first find what happens when I evaluate x in my function, which is exactly the function itself. That was pretty easy. This one is a little bit more complicated. Evaluate x plus h. So I get x squared plus 2xh plus h squared. I distribute the 4. I get 4x squared, 8xh, and then 4h squared. Don't forget your plus 5 that follows along. Then I actually evaluate it in this the definition of a derivative. Okay, and I can erase that. I'll just leave it just like that. So the limit of that as h approaches 0. So I put in f of x plus h. I take away f of x all over x plus h minus x, which gives me just h. 4x squared minus 4x squared will go away. And then 5 minus 5 will go away, which leaves me simply with 8xh plus 4x squared, 4h squared. Then I'll factor out an h, and I get 8x plus 4h, and my h's go away. And now I'm able to limit. Now that I'm not dividing by 0, I have 8x plus 4h. I can limit that to 0, h as h approaches 0, and I get that the derivative, using my definition, is 8x. So today we're talking about differentiability, but specifically where it might fail to exist. And the things you need to know is that differentiability implies local linearity and differentiability implies continuity. This cannot be in the opposite order. Linearity, locally linear things, does not mean that it's differentiable. There could be a hole or something else happening. And then continuity doesn't always imply differentiability either. Just because something is continuous does not mean it's differentiable. So this is an important idea for that differentiability implies all these things. Okay. It's the most specific. It's the Civic of Hondas. So a Civic is a Honda, but not all Hondas are Civics. So in this case, you have to make sure that we are this is so specific that everything else is what it implies. We're going to do some derivatives on a calculator. It's going to be difficult because a lot of you don't have a TI. A lot of you might not have a TI-84, but I'm going to show you another website that you can use for finding derivatives, and then how the derivative, again, how it might fail to exist, and then the intermediate value theorem. I'm not sure. We don't do too much with this, but okay. So why does it matter? Graphs of differentiable functions can be approximated by their tangent lines at points where derivatives exist. Because sometimes we can't find a derivative because we have to follow certain rules. Okay? So a function might fail to exist when one of 4 things generally happen. The first one is when a corner exists. What does a corner look like? Well, it's where one-sided derivatives differ. So if you have a derivative where when x is less than, here, where am I going to put this? Yeah, where x is greater than 0 and you have a derivative that is, I don't know, 1, and then when x is lesser than 0, you have a different derivative. Well, what does that look like? It could look like the absolute value function, okay? So here's your absolute value function. You have a derivative. Oh, here's the function. And look at the slope, -1 and 1. So all of a sudden, you have a location where a lot is going on. There's a problem right there. And so this is what we call a corner. Because there's an immediate change in the derivative. It goes from a negative to a positive. So this is where the one-sided derivatives differ. The one-sided here is -1. The one-sided here is 1. A massive change occurs. Okay, a cusp is where the slopes of a secant line approach from infinity from one side and negative infinity from another. So this one's very interesting. When we read one-sided derivatives, we don't read just left to right. We also read right to left. It's kind of weird, but what we have to do is we have to take a look at what is going on. Oops, let me try this again. If I were to take this tangent line and then this tangent line and this tangent line, or these secant lines, and I start to go like this, what you're going to notice is that the slope of that line goes from looking like that to looking more and more like this. So the slope looks like it approaches negative infinity. Let me clean these lines up. That line starts to turn downward. Oops. And what it looks like is happening is negative infinity. Where from this side, we have the opposite, which appears to be positive infinity. And that is what we would call a cusp. So you have to think about this line sliding this way and becoming more and more negative, while this line slides this way and becomes more and more positive. And that is what a cusp does. So it's kind of like it's kind of like x to the 2/3. This one's kind of like x, the absolute value of x. Okay? It's weird. It's hard to see. It kind of looks like a corner, but you have these extremes of slopes that approach infinity and negative infinity from other sides. Okay, and so this is happening from one side and from the other side as well. There's an extreme, it's an extreme corner. Where vertical tangent's different, it can be either infinity or negative infinity from both sides. So like the cubic root of x. So let's take a look at that graph. What does that graph look like? That graph will look like this. So this graph will do so here when we take our derivatives, what did I use there? I used blue. Let me change this to blue. Here it looks like there's no problems, but there becomes a problem. So here's your line, and the line gets closer and closer to looking like this. So it ends up going like that, and then it becomes like this. And this is positive infinity. And coming from the other side, it's still kind of, positive, and it starts to go like this. From the other side, it's coming in like this, and then it does this. And what you notice is they both look like they're approaching positive infinity, even though I'm going from the left to the right, and then the right to the left, this line, and it's kind of hard to draw it, but I mean, when you move this around, this line is going positive as it gets closer here to positive infinity. And from this side, it's going to, again, positive infinity. So they're matching. You'll notice this, it'll bounce, it'll go like this. Okay? Where this is different on here because this one is going to that positive infinity. But this one is going to negative infinity. So it looks like it crashes and then it flies away, crashing and flying away versus just flying away the entire time. It's just like that nice smooth infinity and then coming back down. Okay. And then the last one, so that's your vertical tangent, your cusp, your corner. The last one is a discontinuity. So if the function is just discontinuous, that is obviously not differentiable, right? So if we get something like this, that would be a discontinuity. So really, we're just going to go through all four, and we are going to, let me highlight this. Oops. That is a discontinuity. And I didn't draw the same one. I just drew a version of one, but that's your discontinuity. So corner, cusp, vertical tangent, and we will do, oh, mess that up. Let's try and change color without changing that one. Nope. Just to keep it consistent. There we are. And here is where, this is where your discontinuity occurs. Okay. So here are a bunch of examples, and take a second, pause the video, and try to answer which ones happened where. Okay, so I'm going to continue on though. This one is probably the easiest, discontinuity at x equals 0. This one is a corner, probably the second easiest to see, corner at x equals 0. This one you have two different infinities happening. You have a negative infinity and then a positive infinity as these lines move closer to 0. So this is a cusp at x equals 0. And the last one, you have two positive infinities happening. So I could literally, if I wanted to, I could just copy this, but I'm not going to. And then you have, let's see, you have this positive infinity, and this positive infinity. As we get closer, So this is a vertical tangent at x. Oh, sorry, what does it say? Vertical tangent, yeah. I've heard vertical discontinuity too, but yeah, vertical tangent at x equals 0. Okay, so here, let's find all the points where this graph is differentiable. It's an absolute value. Looks like there's no scale factor on it, so it is just going to be an absolute value. So I'm going to graph it. Maybe that's too much. I'm going to do a graph of an absolute value. I'll stop it right there. I'll try to match it somewhat over here. It didn't want to do that at first. Okay. And it looks like it has a shift to the right. It has a shift to the right by 2 units because it's x minus 2. And then it looks like it goes up 1, 2, 3 right there. Okay. So this function has a corner at 2 comma 3. So we're going to say the function is differentiable at all locations except at 2 comma 3. And that's it. Okay. Local linearity, it pretty much just says if you zoom in enough to something, it looks like a line. This function has a lot going on here, right? And it's kind of pretty crazy. But if you zoom in, you start to get, just less curvature. And if you zoom in enough, this thing pretty much looks like a line. My software can actually make something a perfect line. So let's see what this does. I mean, you can barely tell that that curve is occurring. I mean, you can kind of see it a little bit. You have a little bit of excess on the left-hand side. You now have it on the right-hand side. So you can tell it's still a curve, but in terms of it being linear, it looks much more linear than it ever did, right? And so this is the idea behind derivatives, is that if you derive it, if you were to take 2 points, you can find the slope between those 2 points. And if you zoom in close enough, you can get those 2 points, right? So if you looked at 2 and 2.00001, you would get that slope, which is pretty much what's happening at 2, which is why we were limiting everything, limiting h to be 0, because that was giving us our almost our location at one spot, one location. So a good way to think of differentiable functions is that they are locally linear. That is, a function that is differentiable at a closely resembles its own tangent line very close to A. In the jargon of graphing calculators, differentiable curves will straighten out when we zoom in on them at a point of differentiability. Okay, and here's what we have. We do have to be careful, and I'm going to show you on the calculator why we have to be careful. What a calculator won't do, let's say there was a hole right here. What a graphing calculator might do is pick a point here and here, and then just draw a line through it and go, yep, okay, I got it. And then calculate, but the issue is that you can't do that because the calculator causes error. Calc may cause an error or skip over an error. So we just got to be careful about that, because this is what it's doing. It's just going, hey, let's go here and here. Oh, there's a hole right here. That's a problem. So differentiability implies continuity. So if something is differentiable, it is continuous, but not all continuous functions are differentiable. Let's just simply go back to this one. Continuous? Heck yeah. It goes down, goes up, no problem anywhere. It's continuous all day long. Where's there a problem? Right here at this point at 2, 3. That's the problem. So again, not all continuous functions are differentiable, but all differentiable functions are continuous. So if there's a derivative there, then it's continuous there. You need to know that. This is important. Memorize. And I mean, you all memorize that as well. Wait, is there another? There's not another slide. Don't memorize that. Just remember that they're locally linear. That differentiability implies local linearity as well. Yeah, let's put it right here. Whoops. Also implies local linearity. Okay. Again, let's see. Yeah. So a calculator causes a problem when you actually calculate it. So, well, sometimes there's a problem. What happens is the calculator doesn't do x and x plus h. It does a plus h and a minus h because it can't do it at the location a, and it does it over an average of 2h because, I don't know, that's just the way they computed it. So some of these you just have to be careful. It could fail. So let's see. Many graphing utilities can approximate derivatives numerically with good accuracy at most points of their domains. For small values of h, the difference quotient exists is often a good numerical approximation of the derivative. However, as suggested by the figure prior, the same value of h will usually yield a better approximation if we use the symmetric difference quotient. That means if you go a little bit before and a little bit after and you average it, then you'll get something a little bit better. All right, but you don't need to worry. This is, remember, a plus h, a minus h, a minus a is 0, h minus negative h is 2h. It's, it's h plus h. So, which is what our graphing calculator uses to calculate this thing called Ender. End derivative is what it does. The numerical, well, Ender actually has changed a little bit on our calculator, and I'll show you. But we're going to use this to calculate some of these at a point, and sometimes we use Ender for Ender when we want to emphasize both function and point. Okay, so let's compute this on the calculator. Well, first off, I'm going to do it by hand, and then I'm going to switch over to my computer and show you how we do it on the calculator. So they want us to calculate x cubed. So wait a minute, I think we've already calculated x cubed, but we'll do that at 2. That's all right, I'll do it again. So f of x equals x cubed, and then f of x plus h is going to be x plus h cubed, which is going to be x plus h times x plus h times x plus h, which I'm going to do some of this math now. I'm going to multiply the first two, which will give me x squared plus 2xh plus h squared. That's still times x plus h. And then when I multiply it again, we're going to get x cubed plus 2x squared h plus xh squared, whoops, plus x squared h plus 2xh squared plus h cubed. I think I did that all right. Let's see. Multiplied everything by x. Yep. Yep. And then h is x squared h. Yep. And h cubed. Okay. So now I need to simplify it. So we get x cubed plus 2 and 1 is 3 plus 3x squared h's, and then plus 2 and 3, so we get plus 3x h squareds plus h cubed. So this is f of x plus h. And I'm going to do f of x plus h minus f of x all over h. I'm going to get x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed, because that's my f of x. I'm going to leave parentheses out of it because I pretty much have it all good here. I'm going to go like this, boom and boom. What I have left over is 3x squared h plus 3x h squared plus h cubed over h. I factor out an h. 3x squared plus 3xh plus 3h squared all over h. We go like this, h's go away. We now limit as h approaches 0, 3x squared plus 3xh plus 3h squared, and this goes to 0. This goes to 0, anything with an h in it. So I now have that the derivative is 3x squared. So the derivative evaluated at, it wants me to evaluate it at 2. So evaluate at 2, I get 3 times. I'm running out of room here. Equals 3 times 4 equals 12. So dy dx at 2 is 12. Or what I like, I don't really like that notation. I'm going to change it up. I'm going to say f prime of 2 equals 12. And there we go. That's our answer. So now I'm going to switch over to the calculator and show you some stuff on there. All right, be right back. We're back now. I have my iPad on the right with my graphing calculator on the left. I had to switch over to this. Let's see. I want to make sure it gets it all because it's going to cut some of this off. But here's your calculator. So I'm going to show you how to do this in calculator. It was asking for you to find the end deriv or ender at x cubed comma 2, and so what we're going to do is we're going to go to y equals, and we're going to type in x cubed, but we want the derivative of x cubed because we want to be able to evaluate that at 2. So if you go to the math key, and we scroll down to end deriv, so they've changed it. So let me update that on the iPad. So
they've updated it. This is old school, but n deriv, and that is under the math key. And on most calculators, it's probably number 8 or so. It's not every calculator, but there we are. So n deriv, we're going to type that in, and look at what loaded up. Now it's kind of hard to see. Let's see if we can. How do I change this view? I want the opposite. Let's see. One second here. View, show large display. Okay, this isn't going to help. But anyway, what I'm going to type in here is I'm going to type in x because I'm deriving it with respect to x. And then here I'm going to type in my function, which is x cubed. I'm not going to derive it. I'm not going to put in 3x squared, which is what I found. I'm just going to actually put in the original function. And so when I do that, I'm going to type in x, and then I type in x cubed, and it's moving for me. I'm not clicking any buttons. It already moved for me. I got to make sure I click this right button. And you know what? This is kind of annoying me right now. So let me just put that down. So I've clicked x cubed, and oh, there we go. That's what I was looking for. And with x cubed, now I want to know what location to graph it at. Now I just want to, I can graph the derivative at all locations. So this is d dx of x cubed and x equals x. What this is saying is derive it with respect to x, derive this function, and then leave it all in terms of a variable. So when I go to graph it, look at what graphs. Isn't that cool? This is actually the derivative here. So let me do zoom standard. All right. And what I can do is I can pull, I don't know why my plots are on. I'm going to turn that off. And I'm going to grab from the table, what location were we looking for? We were looking for 2. And that gave us a result of 12. Look at what it does, 12.000001. Remember, it can't find the slope at 1 point. It's doing 2 points. So we got to assume that that's 12. And that's actually what we got for an answer here. We got f prime of 2 is 12. And that was awesome. So we got what we were looking for. If we wanted any other location, we would then just, oh, what's happening at 3? What's happening at 4? We can do this all day long, right? So if we looked at that derivative and you want to know what was happening at 3, you would do 3 squared is 9 times 3 is 27. Well, that's what they have here. Now let's say you don't want to graph it. You just want to like super quick, easy. By the way, that number is 0. Just assume that anything like that looks like 0. Okay, it's negative. It's 10 to the negative 6, which is 0.000001. So that's 0. Let's get out of there though. Let's just type it into the home screen. We can do that. So we do x cubed. We get out of there, we type in, hey, what location do you want? This, you need to provide a location because you're on your home screen. So you're going to have to type in like something like 2, and then we hit enter. We get 12. There we go. What about if we did it at 3? We said, what, 27? So there's your derivative. This is so easy now that we know how to do this. We're going to derive that at 3, and we're going to get a little bit more than 27 probably. Yeah, there you go. Okay, so that number is 27. What we have to be careful for is where it fails to exist. And that's kind of the last part of our lesson today, is that sometimes it fails to exist and sometimes we can see them and other times we can't. So where could it fail to exist? Well, x squared. Okay, let's see what absolute value of x. So we know that there's a problem at the absolute value of x, right? So let me go over to number absolute value of x. We go to graph this. We get a problem here. But watch this. Watch what happens when I find the derivative. So let me math and deriv. I put this in. I do the absolute value. That's under number. Whoops. And I'm going to graph it at all locations. X, why not? I'll go to my table. Why focus on one when I can focus on all of them? I leave that as a variable. And look at this. -1. Change a derivative to 1. And it goes, hey, 0. You know what it did? It really made a massive mess. It really messed up here. It somehow, let me zoom in. Let's go between y is -2 and 2. It's graphing it there. Why is it doing that? It's just finding a point to the left and right and just trying to connect it through a line. It's like doing the algebra. So what it's doing is it's graphing like this line right here. It's graphing that line right there. You can't even tell because I didn't zoom in enough. Let's change this between -0.1 and 0.1. Whoops, that's not what I wanted. And if I do 1/10 of it, watch this. This is the line it's trying to graph is right there. You can't even see it because I'm graphing it in black, but it's just trying to connect dots. Whoops. I messed that up again. Third time's the charm. That's the line it's graphing, and it fails. It fails. So we got to be careful for that. But again, even on the home screen, you hit dy dx. You throw in your absolute value, and there's a problem there, right? Or how about x to the 2/3? Didn't we have a problem at x to the 2/3? Let's see. X to the 2/3 ended up being a cusp. Okay, let's check that out. Whoops. X to the 2/3. At where? 0? Another problem. All right. So you just gotta be careful. That's why I want to show you how to use a calculator, which is awesome. But you also have to be cautious about what's occurring with it. Now, this isn't the only calculator because you're going to say, well, how does this help me? I don't have a TI-80. I don't have a TI-84 with me, and we're not allowed to use them at the moment. So why this is not adjusting the way I want it to. Uh-oh, I froze this. I want out. There we go. There we go. That's the exact style I want. Okay, that's what I was doing earlier. I don't know how I did that. All right. What are some other calculators we have? Well, we have Desmos. Why can't I not put this down? Okay, it is what it is. Here's Desmos. Let's do a couple in Desmos. Click on functions, and we go to ddx. Okay, let's do x cubed. Let's see what it does for us. Is this a calculator that we can use? Whoops, not x squared, but we want x to the 3rd. And look at, it's the same function that you saw earlier. And so we can derive it, but can we derive it at a location? Does it do a location for us? No, it won't do a location. But what we can do is we can pull a data set from here, what's happening at 2, and we got the answer was 12. And there we go, 2 and 12. Notice at 0, It works. It's fine. Let's try the absolute value. Absolute value. Oh, absolute value of x. See if that causes a problem. Okay, and so that's the derivative at 0. See, it tells me it's undefined. I don't know if you just saw that a second ago. Right there. Oh, undefined. So that's really good that it gives me some type of error. Or how about x to the 2/3? X to the 2/3. And then there's your derivative. That's your derivative, which is approaching negative infinity, while the derivative is approaching infinity. That's not the graph of x of 2/3, right? This is a graph of x of 2/3, but you have your here you have your function decreasing and increasing, right, with a rapid change in the middle, and it's a cusp, but the derivative is taking off in this direction, and then as I approach from the other side, it's going to positive infinity. Okay, what were the other ones? I think it was the cubic root of x. So the cubic root of x, we're going to say x to the 1/3. It's just easier typing that in. So that's my derivative, but what's x to the 1/3 look like? Well, here's x to the 1/3. We graph that. Remember I said positive infinity from this way, because it's still going crazily up, and the same thing's happening from this way. So there's your cusp. And then discontinuity is pretty, standard. The only other calculator I know of that works pretty well is derivativecalculator.net. So you have Desmos and derivativecalculator.net. So here it's already kind of set up for you. You're going to say x cubed, click go, and it'll actually calculate for you. 3x squared is your derivative, and what you have the ability then of doing is typing in the value you want, so 2, which ends up getting us the output of 8 on the original function, but then 12 is my derivative. All right, and so yeah, and so what happens at 0? How about one that at 0? So let's see, absolute value of x. Now we're hoping that it gives us a failure at 0. That would be good. So the absolute value of x at 0. Look at it says that there's an error. That's perfect. So we want to make sure that we have errors where they're supposed to happen, like x to the 1/3. X to the 1/3. It does not want x to the 1/3. It wants me to write it as a cubic root. Wait, why not x to the 2/3? This is not. Oh, because I'm not paying attention. X to the 2/3. I want 2/3 as my fraction. Duh. Okay, sorry. All right, x to the 2/3. There you go. You see the same idea. 0 has an error. And then x to the 1/3 is a cubic root of x. And there we go. And we get the error at 0. So these are the 3 calculators. That's pretty much it. Let's see. We have an exit a lot of this. Let's see where we're at with the notes. I'll just leave it up on the screen for a second. So we did all those, we did all those, we did those, we did those, we did those. This is just a, this is what the quiz will be like. Know these things: corner, cusp, vertical, tangent, discontinuity. Know that differentiability implies continuity and local linearity. Know the different types of discontinuities there. You can use the other type of calculators. You don't need to use the TI-84 because you probably don't have access to one. Well, you might not have access to one, but just be able to follow along that there could be, like this, for instance, is a corner. They're not a cusp, even though it kind of looks like it kind of looks like a cusp, but remember, that would mean infinity or negative infinity would be the derivative. It would take off and go to either infinity or negative infinity. This is a drastic change, but it's drastic enough where you get to see it. It's local, so those are corners right there. Okay, not cusps. Here you have a cusp. I think you know what, this is probably wrong because they didn't put it into absolute value now that I see it. So that's probably wrong. X 1/3. That's wrong. That is supposed to take off if you put this in. Yep, if you put this in that, it would go like this. Okay, sorry about that. I just noticed it. So ignore what's in red from the left-hand side. It would have done the opposite. So I need to update this document. All right, but anyway, I'm just showing you that these things happen. All right, so you can do the quiz review. I've already posted answers for it. You can do the bookwork, and that is it. So good luck.